Good afternoon, everybody. Chris here from RF Venue. Thank you for joining us for our third session of our new weekly webinar series, where we cover RF system design, some product training, tips, techniques, guest speakers, all sorts of fun stuff. And today we're going to be covering antenna placement, really important topic for anyone working with wireless microphones and in-ear monitor systems. Don Boomer, our senior applications engineer, is going to be leading the presentation. So I will hand it over to him. Don, you want to take it away?
Thank you all for joining us again. Sitting here sheltering in place. Have a terrible problem. I've run out of Fig Newtons, but we're going to try to go on anyway. So here we go. So the topic for today is practical solutions for antenna placement. This photo here, if you're from Los Angeles, is Mount Wilson, where there are 25 television stations and a little more than 20 radio stations all beaming down onto Los Angeles. Lots of antennas. Lots of fun to try to find open space, especially out on the street. But anyway, I digress. What we want to talk about here are best practices. So we want to make you aware of a number of things. Obviously, you'll have to work all these into your systems, but we just would like you to be aware of all these points so that you can get the best performance out of your gear as possible. Keeping wireless mics on the air is basically avoiding that last straw that breaks the camel's back, right? So what we want to do, we want to try to remove as many straws from the camel's back that we can do simply by working a little smarter or employing some low-cost things, because the last straws at the end can tend to get to be very, very expensive. So we'd like to work a little smarter and end up with a little more reliability. So the first one that we want to talk about is line of sight. And what that means is that your transmitter can see your receiving antenna. You want to, in this case, if you have an audience, you'd like the antenna to be just a little over their heads or the performers' heads. You don't want to be shooting your transmitting signal through bodies. They will block it. Also goes without saying, if your antennas are in a rack and that rack is 2 or 3 feet high, obviously people getting in the way are going to block that signal. Likewise, very, very good practice to have your transmitter and your receiving antenna in the same room. A lot of times people will put equipment in closets. That's fine, but you do have to run a remote antenna out into the space where you're actually transmitting. Otherwise, you're going to lose an enormous amount of signal. People ask me about all the time, speaking of line of sight. Upper left there, we've got a baseball field. Now, in this case, I think most professional baseball fields, the netting is just that. It's whatever it is, nylon netting. But if you're trying to do wireless, at a high school or a little league or something like that, and they have chain link fence, while you can see through that chain link fence, you can't broadcast through it. You have to be over the top of it. So that's something you need to be aware of. Likewise, bottom left, the football field. Here's maybe a high school one. We sure can't put the antenna in that cage on top of the press box because that's going to block it effectively. A lot of people would put the antennas maybe on the press box wall or even inside behind the glass. We'll talk about that in a minute. But you need to be able to draw a straight line from transmitter to receiver. So if you're standing out on a field with a wireless mic in your hand, you need to be able to draw a straight line back to the antenna. Up on top there, people ask, how does it go through walls? And the question is, what's your wall made out of? If you have a wall with metal studs, that's going to be much, much more difficult than if it has wooden studs. And the exact spacing of those studs is also going to be a consideration. So if they're on the standard, 16-inch centers, that's going to block your signal a lot more than if they happen to be on 24-inch centers, which isn't quite so common. So you kind of have to know this when you're setting up if you need to go through a wall. And the other one I get all the time are these movable partitions to block off big rooms into small rooms. And again, the deciding factor here is, what is this made out of? You know, if it's wooden with a metal frame and that frame is at least, 2 feet, it's going to be one thing. If there's metal reinforcement down in those panels, that's going to be a totally another thing. So you may have to research that if you can, best you can anyway, to go back and see just what those materials are. So here's the deal when you're trying to transmit through openings, right? So here's a wall. We're transmitting at a wavelength. So in the US, and you'll have to adapt this according to where you are, but in the US, we're running wireless mics from 470 to 608. So that is a wavelength of a little more than 25 inches to a little less than 20 inches. Imagine that wave trying to penetrate through an opening as a solid object. Imagine it's a metal rod. You have to be able to push it horizontally through that opening. So as long as that opening is bigger than your wavelength, then the radio signal will go through that opening rather nicely. However, if it's smaller, then it won't. So back to that chain link fence. While it's very porous to water, would go right through it, your radio signal is not really going to go through it unless the links were roughly 2-foot squares. Where you see this is in your microwave oven, right? If you look in a microwave oven, it's got a glass front and it's got a little metal screen in there. And the opening of that screen are so small that it won't let the microwaves out, but it lets visible light through. So you can see what you're cooking or burning in my case. And that's how that works. So it's just the fact that the openings are too small. So as long as your opening is at least the wavelength, you're probably going to have a pretty good shot at going through it. So trying to penetrate things. Here's a chart. This is very generalized because, as always, it depends exactly on what you're dealing with. Glass is pretty forgiving unless it's treated glass. So these new e-glasses, if your glass has some kind of a coating on it to prevent ultraviolet, then expect it to block the signal a whole lot more. That's just something you're going to have to research if you have to go through glass. Again, back to that press box. So we have a lot of people that put the antennas on the inside, and most oftentimes that works. There's not a big amount of loss, but just understand that you really need to explore a little bit and determine, if you can, the properties of that particular glass. Some of these other ones here, wood, brick, concrete, have quite a spread in them. Pretty much that can be related to the water content of them. If they're wet, they block signal a whole lot more than if they're dry. And then of course, metal is basically, that's the end of the story. It's not going through. So the question here too is water. As I mentioned, if your concrete's wet, if your bricks are wet, if your wood is wet, it's going to block the signal more than if it's dry. This is why submarines have to come up and stick those antennas up in the air. It doesn't work through the water. But then, of course, the other water in the world of wireless microphones is the water bags that are holding the microphones. So as we can see here on the left, this person, Invisible Man, I guess, is holding that mic about the way people do, but still, just holding that mic with your hand right there is going to block some of the signal, probably 6 or 8 dB of the signal. Even worse if he cups the very end of it where the antenna is. So I strongly suggest that you educate your end users the proper place to hold that microphone. Likewise, belt packs. If you're going to transmit, well, depending on which side your receiving antenna is, but if you're transmitting through a body, that's a lot of water to go through, salt water. So, and it's very much going to depend on size. The little 99-pound guy here is probably only going to block half as much signal as a 300-pound guy. And I do want to point out here, another best practice is make sure that those belt packs are like they shown here, on a belt. What you really don't want to do is stick that in your pocket. You don't want to get that antenna really close to your skin. Bad things start to happen. And also, I see a lot of times pastors like to roll that little antenna up and stick it in their belt or something. You're losing an awful lot of potential by doing it that way. So best to do it this way. If it's a guitar player, put it on his strap, but not in his pocket, especially if the pocket's got a cell phone in it, but that's another story. So here's another thing. You can be too close to your receiving antenna. And what happens is you can send such a strong signal by being close that you overload the front end of your receiver. So think about it this way. If you and I were sitting, having coffee, sitting across from a table, speaking in our normal speaking voices, whatever that is, then that would be fine. We'd be speaking to each other. However, if I got up, walked over to you, and in that same level, that same loudness, spoke to you, but an eighth of an inch away from your ear, you would consider that screaming. Even though the level hadn't changed, what happens is the distance changes. So you want to kind of observe these. These are sort of basic recommendations. As always, it depends on everything, but you want to keep your transmitters from ending up very close to your antennas. One place this could happen, especially if you have your receivers in a rack on the stage, let's say in the wing of a stage, you're at Monitor World and that's where they are, and you have a performer getting ready to go out onto the stage, standing there, and he's leaning up against your rack. Boy, he's really close. Bad things are going to happen. So as you can see, the distance is proportional to the gain of the antenna. So very high gain antennas, like the helical antenna on the bottom, you need to be farther away from. Paddle antennas are kind of medium, and the whip antennas would be the lowest gain. So you want to kind of remember these things as you can, and minimize the possibility that that can happen. And of course, you also have to consider not only your intended transmitter. A lot of times, there's comms or walkie-talkies or something, and boy, you don't want a security guy standing up next to your antennas keying his FM radio. That's pretty darn powerful. Even though it's out of band, the signal is so strong. Again, he's getting up to an eighth of an inch within to your ear, so he can just be overpowering your receiver. Another thing you want to do is you want to keep your antennas away from metal. I have a lot of people that want to put their antennas up in a lighting truss. So we're going to take a look at these here. There's a few different things that are happening. So what looks like the biggest offender, wow, all those helical antennas are right up against the truss. These antennas have a planar reflector in the back. Basically, they're blocked from the back from anything picking up. So in the case of our CP beam antenna, you can mount it right up against the truss and there's no interaction. The other two antennas that you see above it, that's actually, if you have to mount it on a truss, that's the way to do it. Get it away from the truss. In this case, also the bottom of the antennas, or the pattern underneath, is somewhat dead. The Omni antenna on the top there basically is a donut shape. So it in a horizontal plane, it's 360 degrees more or less, but it's a little dead on the top and bottom, kind of like a donut. Likewise, paddle antennas tend to be a little dead on the top and bottom. So while this is near the metal, we are taking advantage of the patterns of the antenna and kind of locating the metal to the dead side. I would also say that this is going to affect your transmitters. A while back, I worked for a company and we developed a digital wireless microphone, which we were always testing. And one of the things that we wanted to do was test maximum range. I think we rated it at 300 feet. And obviously we didn't have a Faraday cage that big to measure it. So we would go outside in the parking lot and measure the distance that it would transmit. And one of the things that I learned as you walk down the side of the building, where the big metal loading garage doors were. As you walked close to those doors, bad things would happen. You kind of end up in shadows and everything falls apart. I'm saying this in the case that you have big metal stage pieces, or the back of your stage has a roll-up garage door or something. You need to take that into account. That is going to negatively impact what's going on. So just something you need to be aware of. And here's another big one. No antenna farms. This is what you don't want to do. You don't want to put a bunch of antennas together in close proximity. They really need to be spread apart, at least by a wavelength would be a good idea. But there's some bad things that happen when you put antennas together. So the normal rule of thumb almost always is fewer antennas work better than many antennas. They steal power from each other. Obviously, if one antenna absorbs the power out of the air, then it's not there for another antenna. That's pretty small, but it can add up. They interfere with each other. So when an antenna is receiving, right, it's receiving the signal and it's generating a current in that wire that's the antenna. And when you pass a current through a wire, it generates a magnetic field, and that magnetic field gets into the antenna that's very close to it and generates a current that you don't want there. So you're getting a little interference from each other. And the other thing that most people aren't terribly aware of is that when the signal goes into that antenna, it's not 100% absorbed by the receiver. What happens is receivers have something called a local oscillator, and anyway, it kicks back a little of that power. So maybe 10% of the power that's going into that antenna is reflected back out of that antenna. And so it's essentially transmitting that signal into the antenna that's next to it, right? So there's some more interference you'd like to avoid. And then when you start putting a bunch of antennas together, you change their pickup patterns. You're actually creating an array. Now, if you've ever looked at the traces on your paddle antenna, you can kind of see, you see the antenna, the traces. So there's long elements and short elements, and they're very carefully calculated, and there's paths that block in between. Anyway, that's all very well worked out to create a certain pattern. But just like making a line array with speakers, as you stack your speakers together, where they go ends up being different. So the same thing, when you put a bunch of antennas together, who knows what it's actually where it's actually going. So you also, in this case, you can't set the antennas properly for proper polarization. There's just no way to do it. If you're not familiar with that, if you get a chance and go back and look at our first webinar, we discussed that and exactly how that works. There's a thing called polarization crossfade that will take you off the air. And it's definitely going to be a problem, another straw in the camel's back when you do it this way. So if you're not using antenna distros, you really need to space those receivers apart. I've been to lots of places where they've got 2 or 3 or 6 receivers, not rack mounted, just on a desk, stacked on top of each other, and it's interfering with each other. You could split them a couple of 3 or 4 feet apart, but by the time you got 6 or 8 or 10 receivers, that gets to be an awfully large table. So the right way to do it is to use antenna distribution system, resolve the needs of all your receivers down to a pair of antennas or multiples if it's zoned. You want to do that. And then I'd like to point out on the bottom picture here, bottom right, another cardinal sin, that you have the in-ear transmitting antennas right next to the wireless microphone receiving antennas. So you are screaming in the ears of those receiving antennas. You can put the units in the rack, that's okay, but you really need to separate the in-ear transmitting antennas from the wireless microphone receiving antennas. How far? Well, as far as possible. I mean, 6 or 10 feet is reasonable. Double that's even, it gets crazy. But you want to get them as far apart from each other as you possibly can. Let's talk about antenna patterns and polars. So polars are the representations of the antenna patterns that you see on spec sheets. So you may not be familiar with these terms. A lot of them are used interchangeably. There's some tiny differences, but we don't care about that. So horizontal is also called azimuth, is sometimes x-axis. The vertical is sometimes called elevation, y-axis, altitude. These are all sort of interchangeable words, certainly for general purpose of what we're doing with antennas. So here's what a polar looks like. In this case, this is the azimuth. This is the horizontal pattern of the LPDA portion of our diversity fin antenna. If you're not familiar with looking at these, this is on axis. This is straight ahead in both of these. So it may look like on the polar that it's pointing up to the ceiling, but really this is intending that you lay that on the horizontal plane. So sometimes that's called bore sight. I mean, it's straight ahead. 12 o'clock on this kind of a polar is like you're sighting down a rifle barrel. That's where the strongest part of the signal is. So this antenna has a beam width of what we call 140 degrees in the horizontal plane. Now there's also a vertical polar, but we'll just talk about one at a time here, because when you understand one, you understand them all. So we call this 140 degrees. And so that means 70 degrees each side of on axis is the 3 dB down point. That's the half power ability of the antenna to receive. But realize that that's not the only place that antenna is picking up. It's picking up outside that blue triangle. But you can see that to the back, there's 10 dB of rejection. So the way these antennas work is that it's a zero sum. You're basically cutting off the ability of the antenna to operate in one direction, and you're shoving it into the other side. So if you cut off 10 on the back, you add 10 to the front. So the more directional an antenna is, the further it appears to reach out. Although antennas don't reach out, they catch. So you can see that this antenna still got pickup on the sides. It's got rejection in the back, and you can use that to your advantage. You'd like to use the back side, the lower sensitivity side of an antenna, and point that to any potential local interference that you have. Back to that first slide where we got the television stations in Los Angeles. In a lot of major cities, almost all the television comes from one hill someplace. So if you can, and it makes sense, you might want to point the backside or the low sensitivity side of your antenna towards that if you're close and you're getting a lot of interference from TV. Or there's something else in your room. You have an electrical closet with a bunch of crazy stuff going off, or you have a lot of video gear or something. Anyway, just understand that you have a hot side and a not so hot side. So use that to your advantage when you can. Okay. So this is really the question, right? Where do I put my antennas? How do I make this work? Well, again, it all depends. It all depends what you want to do and what you don't want to do. So maybe you're thinking, well, okay, we'll put it on the back wall in the center and shoot it at the stage. And that's perfectly reasonable. You're going to get this. So you're going to get, obviously in the blue field is the strongest pickup for that antenna, although you're still getting some pickup in the red. And of course, we're not counting for the walls here, which would be blocking it, at least somewhat. So that's kind of what you're going to get. Now, that's fine if you don't need rock solid pickup where the stars are. Maybe you actually want to reject something there a little bit. Maybe you've got who knows, something with motors or something with computers, or you got a video desk or video production or something. Anyway, you're going to get a little less pickup there. It's not going to stop, but it's not going to be nearly as strong as it's going to be facing forward. So maybe you want to do it this way. Maybe the corner of a room is a good place in a rectangular room if your desired pickup is the entire room. You want to catch everything in the room. So you're going to get this, and you see you don't have those, I won't call them dead, but less strong areas to the back that you do if you did this in the center. So it just depends. Is this what you want to do? Is this what you don't want to do? Either way. And then a lot of times I get asked, how about if I put it in the wing on a stage? Again, this has a reason to do it and a reason not to do it. So in this case, you see we've missed a lot of pickup from half the audience. That means we're not going to get their cell phones. That means we're not going to get the video production table in the back or whatever happens to be there. So this might be a strategy that you could use. And then again, if we're doing in-ear monitors and microphones at the same time, here's a way to think about that, because we don't want to point the antenna, the transmitting antenna from the in-ear monitors directly at the receiving antenna for the wireless microphones if we can avoid it. So in this case, that polar happens to be for our CP beam helical antenna. Most helical antennas are going to look something like this. The blue, of course, is our diversity fin. Most paddles are going to look like this. If you're using two paddles, then you're going to make two triangles, and you can kind of figure that out. But this would be a strategy. Now, you may also have to move that in-ear transmitting antenna. Maybe it has to come from the back. Maybe all this is coming from very close to your sound booth, and we're gonna turn that 90 degrees. If you have to do that, it's a good idea to put your in-ear transmitting antenna a bit closer to the stage than your receiving antennas. So you can take advantage of the fact that antenna is a little more dead on the sides. So again, we're just trying to take another straw off the camel's back. Maybe you really need to avoid everything in the house except the stage. This would be a case where, in this case, I'm using two helical antennas, one stage right, one in the right wing, one in the left wing, and I'm covering the stage. I'm purposely trying to avoid picking up anything in the house. And this also lets me maybe attenuate the antennas. I get a nice strong signal on the stage, but maybe I can pad them down a little bit and avoid, whatever. You may have another transmitter, TV stations. In other words, I can avoid outside rogue interference that I don't want by simply turning down my antennas. So this would be a strategy when that's your problem, when what you need to do is avoid interference, and you don't need to cover the whole house. Obviously, this isn't going to work for a theater or a church, where the pastor runs out through the congregation. That's not going to work. So again, it's just you just need to make it work for pretty much whatever you need to make it work. So really, once you understand the polars, you just need to take your floor plan, and you need to create the angles of the antennas and place them where it makes sense. Place them so you can cover what you need to cover. Place them where you can avoid what you would like to avoid as best you can, and that's pretty much how it goes. And it could be, down the one I've got in the bottom right corner is a casino. Maybe for this, we're going to use a zone system. So, who knows how many antennas are going to be in there, depending how big this is. But, if it's 4 antennas, if it's 8 antennas, if it's 20 antennas, again, we're going to look at the geometric pattern of that antenna, and we're going to lay it so it makes sense in that room. And that's basically the the practical application of how you look at these polars and decide where to put your antennas. So remembering those best practices, especially line of sight, get it up where you can see it, focus the antenna to where it needs to be, and possibly don't focus it where it needs to not be. Avoid what you can when you can do that.